Thanks. That was easy. Excellent. And I guess we're good to go. Sorry to interrupt. You can go ahead. And what were you saying?
I don't know.
So where I am is I want to, after that, I want to, hoping in the next couple of days to take a look at the whole function deal, which I'm assuming based on last time we met works not unlike subroutines in BASIC.
Correct.
Yes.
Okay.
When I came to it, I've had a lot of students in the past not grasp everything from POE, and I know why POE teachers just kind of ditched voids and functions and all those things. I don't even think he's really in if statements much anymore, which is wackadoo. But anyway, I can kind of look at my students, and if I see eyes that look like glazed donuts, then I just don't do voids at all.
Okay. Well, and I know my kids did no programming last year with the guy, with the teacher who was doing POE. So maybe that's part of the reason things are taking so long. Everything is new for them.
Right.
In robotics.
You may share the PowerPoints with them so that they've got things to look at. If you've got some of your higher end students that maybe do a little bit of programming, especially if you do anything like Arduino or that kind of stuff, you're going to see voids all over the place. So some of those kids already get the concept of what a void is, but
I don't know what you're talking about, to be honest.
Voids are subprograms.
Okay.
Different than tasks. What I really like to add in CIM that they don't do in POE is I like to add another task. The big thing between tasks and voids are subprograms where it's going to basically leave your program and go run something and then come back, and it can be used all over the program. So for like a blinking light type thing. A task, you got to be very careful because tasks, you can actually run more than one task at a time.
Okay.
So once you call a task to run, you could have 10 tasks running at the same time, and you could end up with a lot of conflicts. So that's the only thing that starts getting a little bit tricky. In the curriculum, there is a PowerPoint called Emergency Stop, and in the Emergency Stop, they show them how to make a secondary task.
Okay.
Yeah.
Cool. So both of these would be kind of functions, and it's just two different ways of implementing them. One runs concurrently with the with another task, and then the other one leaves a task to go do another task and then comes back.
Yes.
Yes. Yeah, I guess that's a good way to look at it.
The only thing I'd be careful, I'm not a programmer, so I don't know if multiple tasking actually falls under the category of functions. I don't know that it does. I think a task is a task. Category.
Okay, I just shared my screen with you guys. Can you see it?
I'm not. Yes.
Yeah. Okay. Give it a second. The reason I guess I'm just showing off to Jim too, because I have a kid this year who programs in C++. So he's doing some amazing. I'm giving the kids tasks to do, giving them programs to write. And what he's doing is he's writing everything. He's actually, so here's an example on my screen. Make a robot go forward straight, turn, no, that's not what this is supposed to do, I don't think. Yeah, I think it is. Yeah, it's a simple, make it go forward straight. I'm getting him to learn how to use outputs, getting him to learn how to use the motors.
Okay.
So what he did was he went and he made a different task. He made variables for speed and time. And for instance, so he even went, and I got to sit down with him because I don't totally understand this, and maybe you do, Jim, but he gave each task a set of initials. So he renamed all the tasks so that all he had to do was do the stop task forward motor, and then stop both motors. Then call that stop task. He has a task called stop task. There's one for SM. There's one for FM.
There should still be a task main somewhere down below.
Is there? I don't. Oh, there is. Yep.
Because as soon as you start the program, it's going to look for task main and it's going to run that. In his task main, he's calling for other tasks to run.
Correct. So here's his program, and basically all this says is until the bump switch. So wait for the bump switch, then wait 1 second, and then speed 64, do start motors, then stop motors, wait, then turn left, then turn right. So he's basically simplified task main and complicated everything else. But
Basically what he made was his own natural language.
what's that?
He basically made his own natural language.
Correct.
So
So
if you look at there where he has pound define,
yes,
that's where he's defining to be able to use the word start mode or start
Right.
motors.
Right.
Starts the, so anytime he types the word, which is it's a lot of counterintuitive to most of us to do wrote about C. It's not necessarily for C++ and for Java, and that's the way things have to be done in other languages.
All right, so basically what he's done is he's given a natural language name to
yes,
a set of commands, and then he can just call up that commands with that
correct. And
turn left, turn right.
he originally
That's what
tried,
natural language is.
yes,
That until touch and that kind of stuff, you can actually step into that, and it's that one until touch is actually like 15 lines of code.
he tried to call it start task, and he tried to name them forward. He tried to name them things that were in the program, and it blew up on him.
There's a lot of reserved words.
Right, so he couldn't use the reserved word, so he used these initials, FM, SM, TL, and TR.
So basically then when we load up Robot C, there's a bunch of these chunks of code
Right.
that are already defined as a command, and then we just get to type in the command, and in the background there's 15 lines of code or whatever that's already
Correct.
Now, because this was originally designed to also be in our 8th grade class. So Robot C,
Right.
actually, natural language doesn't exist except for Project Lead the Way. So
Okay.
any other schools that are not PLTW and just have Robot C, they don't have the natural language. My sim kids, I try to avoid having them write natural language. We do that in POE, but for the most part, I've tried to get my kids out of the habit because it's a simplified code. It doesn't exist in the real world.
So Jim, how do I get this? How do I see what's behind this without running it first?
What do you mean?
Is there a way to do that? I want to see what's behind this. Is there a way to do it? To see the source code?
Yeah, can't you go up to View or Robot or something?
Yeah.
I know you can do it while you're running it.
Right, and I'm not connected.
Step through. Yeah, I wish it had a simulation component to it.
So just because maybe I'm not following completely after all, but because I know you guys have like a command that's like until.
Yes.
Now on the Tetrix version, I don't have that. So is until like an example of something that's a natural language, and then because I don't have it at all, my kids are doing it more like you would in normal program because they've had a while loop.
Yep.
But you can actually, the Robot C version that you have, you should be able to bring in natural language. Yours just doesn't have it by default. Chris, show him where.
Oh, okay.
If you go to Robot and you choose platform type, make sure you've got the VEX2 Cortex. You should be able to come down here and choose natural language, Project Lead the Way. And when you click on that, when there's a check mark there, natural language will show up over here in your text functions box. Like so. It'll look like that. Then when you open natural...
I'm looking right now
to
see if I can get it. So you said that's under Robot?
Robot. Platform type.
And then platform type. Of course, I have slightly different platforms. Yeah, so see, I don't have natural language because I'm using Lego Mindstorms as my platform.
So then the software didn't come from Project Lead the Way, so it doesn't have the natural language.
Right. So I'm not doing any natural language, which you're saying really for sim is more appropriate anyway.
It works better for me because the first time my kids see it, so it's a little bit easier for them. But in Jim's case, sim is one of the last courses, so he's doing it more C++, more the without the natural language.
Right. Okay.
And getting away from the untils in using if-else, if else's and stuff like that.
Right, right.
So
But I still don't. I don't have them write the code like your kid over there wrote the code. I don't write it in true Java or C++.
Really?
I'm still writing it in kind of a bastard version. I'm just not having them using an actual language.
No, and this kid is blowing me away. He's showing me things that, and I'm telling him, save it in that folder on your desktop. I'll buy you pizza on Friday because I want everything. And look at what he's got. He's going through and he's remarking it all for me, and he's making, and he's just
awesome.
Happy as can be to go through and do all these things. And then I'm going to share this folder with Jim, and then I can have Jim explain to me how it actually works.
See, there's a lot of smart things that he's doing there. If you look at each one of his tasks, before he leaves the task, he's stopping motors.
Yes, right.
See, the problem is, look at your very first task there, your task FM. The problem there is it says start motor,
but it doesn't stop.
That task, those motors are going to keep running.
So really, this should happen.
Well, you can't very well do that because then it's starting them and closing them up. So one way or another, he has to have some kind of error coding in there that's taking care of that. But the kids don't think about that stuff. Just because I asked an if statement to stop, just because I asked a while statement, just because I asked a task, anything if I don't actually turn off the outputs, they'll keep doing whatever they were doing.
Got it.
Right. Yeah, we've noticed that with ours.
And that's a good thing for the AGV, because usually if the AGV is turning one direction, even if it's lost the line, he'll keep going in that direction until another if statement one way or another gets met. Because otherwise, if you had it written like you really should, and you had an if, an else if, and an else, that type of thing, as soon as he loses a line, he'd stop. He just wouldn't do anything.
Gotcha.
I tell you that the funny thing that's the biggest, I think, issue with my kids is not realizing that they need to make some of this stuff loop, or that they have to have like they just don't have a delay between their commands, and they're like, oh, I told it to go, and then to stop, and it did nothing. And I said, well, you have this one if statement to check, and it told it to go, and then it reached the end of the program, so it immediately stopped, and it never. You never saw it go anywhere.
Yeah. Yeah, my kids, when my kids start, they do the same thing. It's they do the exact same thing with, oh, okay, I guess I got to wait or put a pause in there so that I can see it.
Right.
So does that...
The Firefly program was a lot of fun. I only had one group come up with the same solution as me, but it was an interesting little thing trying to realizing that we could do these like really, really short waits in a count to basically have the thing spin in a circle, and ultimately every 10 microseconds check the light sensor value, and then run the motor for 10 microseconds, then check it again, and then run the motors. And then when we ran it, all you saw was the thing just do a 360.
Really?
But in that time, it checked that lights. Yeah, because it just was looping so fast. You know, there was never any pause in the motor. There was just these wait commands. And so it kept running the motor, but it just then checked that light sensor. And then we put a command in there that was, if the current light sensor value is greater than the stored value, store the new, what you're reading now. And it just do this 360, find the greatest one, and then they could do like a while loop that said, okay, now run the motors in a circle while the light sensor is reading lower than the greatest value you found. Come around again, point right at that light sensor, and then the next thing was just go forward until the touch sensor hits the stand. And it just, well, most of them did sonars because it was easier to get the sonars to pick up than hit it square enough to hit. I don't know how the VEX bump sensors are, but the Tetrix, if you don't hit it square on, it doesn't detect squat. So the touch sensors are pretty worthless.
Well, that's cool. That's awesome. And your kids enjoy it.
Yeah, I think so. So hopefully I'm going to do that, do the functions. I want to use your guys' idea of giving them the pseudocode. We were already starting our project when you gave me that idea, but I'm hoping to give them some pseudocode and then have them write the code
Good.
Using some functions, and then have them go on that delivery system project. And then I'm not sure what we'll do. I guess I need to look at the curriculum and see what's supposed to come next. But I know I skipped a lot of classroom stuff, so we'll probably do some of that on the Kaizen and that whole presentation business you guys talked about.
Mm-hmm.
And I can't remember if it was you or my other one that talked about just having one giant Google Doc and letting everyone throw in their presentation. And so then when we do the presentations in class, it's just one kid goes up and goes until they get to the end of their slides, and the next kid goes, and it speeds up the whole.
I don't even have the kids do the presentations anymore.
Yeah.
The kids, I make them make PowerPoints. I have the kids make the PowerPoints, and then they share them with each other. And then they have to make sure their PowerPoint has the, so when you're, I don't know if when you use PowerPoints, the notes section is down there at the bottom. They have to put all the notes and everything down there, and basically they've made a nice PowerPoint that could be presented. I just don't have, 10 minutes per kid per topic, 30 topics. I can't see absorbing that much time. So they share them with each other in one great big folder. They take the document. They have to read each other's PowerPoints, and they've got to get that information. So I just simplified it. I still do the presentation. I still have them created. I still critique them on how well was the PowerPoint done. But I've got so many kids, they're introverts. They're not very good at presentations anyway. So if I kid on how well he does a presentation, it didn't really have anything to do with SIM anyway.
Okay. Must have been a POE one then. They talked about creating just a super, having everyone work, every kid do their own presentation, but them all work on one document. And then when they went to the presentation, you're not looking, okay, which one's yours, and you load it up, and how did you send it to me? You just have to open the one presentation that you've shared with all the kids.
Right.
Yeah.
And
you could have them upload it to the virtual academy, or not virtual academy, that's all, the LMS/virtual academy.
Yeah. And that's exactly what I'm doing with my POE class. This is my school has to use Schoology. So what I have them do, I passed out to them a energy sources template PowerPoint. And what it is it's basically a PowerPoint that's a template. So I put this out there. They open up this template that's a PowerPoint template. They put their 3 or 4 slides into that template. So each kid goes in and puts what type of energy, who, and then their 3 or 4 slides. They delete the rest of the slides, and then I give them a place to hand them in. And I even go so far as to have them give me, I do a 10-minute lesson on how to write a multiple choice question. They hand in to me 2 multiple choice questions in a Word document. Then I put that whole PowerPoint together. I take all their PowerPoints. They handed it in last class. They hand in all those little 3-slide PowerPoints. I put them all into one. Then they hand in their questions. And then later on next week, I will put that PowerPoint live and give them a homework assignment. Go take this quiz. And I'll take I'll take 10 or 15 of the good questions, make a quiz out of it, and then they have to sort through the PowerPoint and answer at least one or two questions from each form of energy so that I know they've gone through it all.
Right.
And that way, cool. And you save a ton of time. Number one, I can give it for homework because most of my kids have access to a computer during a free period at home. Whereas if you didn't, you just give it in class, and it takes 15 minutes versus 3.5 days to do presentations. And some of them really don't like to do the presentations. And since SIM and POE is one of my end courses, so POE, the kids are towards the end of the class, they're going to start doing presentations. So they're going to get the presentations. It's just that I don't like to use the time in class right up front early.
Right.
So that might be one way to do it.
So anyway, so what should I be looking for after this delivery system, and of course after I go back and get this presentation thing done in some fashion or another?
Okay. So then after you do lesson 1-3, you do the transportation system, you do the transfer system. After you,
And now the transfer system, let me back up. The transfer system, from what I think maybe you showed us last time, or maybe I saw some videos on my own, I was assuming it was originally like a robot that would travel somewhere, grab something, and bring it back.
nope.
But it looks like it's more of an assembly line
Yes.
type situation.
Yep.
Okay.
I think it was meant more to be a transfer system in a factory, a manufacturing plant.
Okay.
So it was more. I know teachers who've done different things with it.
Uh-huh.
So it's not that it's wrong, but I think it was more of a. I like to teach things like value-added tasks and non-value-added tasks, and transfer systems are the biggest non-value-added tasks you can ever have. You're just
Well,
moving stuff around, not adding value to it. So you want to be able to be efficient and do it as quickly as possible.
Yeah, I really would like to take a look at that because I thought
Sure.
that was pretty neat what you talked about with, I guess, bringing in, one of you two bringing in some actual industry guys and
Yeah.
hearing the kids talk about value-added tasks. And it's like, okay, that's cool. If I can pull that off, I'd love
Sure.
to. So, and I think, too, we've been working with the exact same robots for like 2 months now.
Right.
They haven't done any hardware changes to the design, and a design they looked up online.
Right.
You know,
right.
so I think the fact that we can have them tear that down and actually build a transfer system and program it, I think really is a lot better than just coming up with another program for the robot to do.
Right. So that's probably getting a little old too. They're probably looking forward to, give them a brand new. Say here's the problem. You have to come up with something, and don't show them whatever you do. Don't show them the videos ahead of time because they'll just they'll all look like that. Give them the whole shooting match, the whole showdown, and say, here, this is what I want you to do, and do it most efficiently. And then as they go, it's a learning process the first time too.
Now, I guess I need to have them actually build something then, right? There needs to be multiple. I haven't looked at this activity really.
Yeah.
But based on what we talked last time, there has to be some kind of multi-step build process, and I guess that could be as easily as putting some Legos together to build something.
Right. And if there's an example. I'll show you the example that's in the that we have for VEX. And you're right, it can be just about anything. Back when we used Fisher Tech, we used to make no-go gauges to check them to see if they were right. But here's the widget that they're manufacturing. So they have to manufacture.
Okay.
The transfer system has to manufacture this part. And it has
2 assemblies and then a finishing operation.
Right. So you have these parts for step 1, for the sub-assembly.
Okay.
It does this. Here's the parts for step 2. It does this. The parts for step 3. If step 1 and 2 assembled, you put them all together.
And I'm guessing most of the actual assembly then is done by hand, and the system just takes that sub-assembly and transfers it to the next station.
Yep. The video.
Want human interaction. The entire thing is based on cost. So not only is it the cost of the material that they use, but it's also they have to incorporate the amount of time that it took them to manufacture these 3 widgets. So it's a competition from one group to another, not only to make a system that's cost efficient for machinery, but also find a way you get to talk to them about how much does each employee cost and how much faster would we have to make it to be able to afford a second employee. Is this best done by one person for the amount of time that it takes us to do it? If I add another person and we only make it 20 seconds faster, was that person worth having on staff? There's all kinds of really neat conversation components that you can have with that. But yeah, they're supposed to go through. It's actually easier when they're tearing it apart is to find the cost of the entire thing. Well, that's going to be the hard thing for you with your Tetrix is we have a spreadsheet for the VEX that has every single piece broken down into its cost.
Okay, I was about to ask about that. So when they build the sucker, they have a spreadsheet, and it's like every screw, every nut, every flat piece, it all has a cost, and they count it up when they tear it down and see what the cost of the sucker is.
It's so much easier to do it when you're tearing it down because then all you do is just kind of group things together. They make so many changes while they're building is to maintain.
Right.
But they get the thing ahead of time so they can say, oh, that ultrasonic is $30 and these line followers are $15, whatever they are.
Yeah.
And they get to make a decision right off the bat on is a conveyor belt the best way to do this? Is it better to do it with some kind
Right.
of linear system that's slower but is more cost effective?
Right. And so I guess if I wanted to, so I would need to come up with some way to do that, some kind of spreadsheet. And I guess I'm actually kind of thinking, it's like, well, if I want to take the easy way out, I'd do something like, okay, weigh the framing and say, okay, the framing based on weight, that's how we figure out that cost. And then the motors and the sensors would all have set costs. But maybe the spreadsheet thing would just make a little more time to set up. It might be better.
You may find on Tetric's website too. They may
The
have,
actual cost
if you went somewhere, yeah, if they went to a Tetric's website, you could have them create a spreadsheet of just their parts.
Okay.
Possibly.
Right, right.
Because
Assuming they would sell it all piecemeal or whatever.
right, and we did. We went over this last week too a little bit, but all of the resources, the presentations, the resources, that spreadsheet that we showed you last week is right, and of course I'm not going to be able to find it now. It's in the cost overview. And that's where it differentiates manpower. At the top, we put in how many people worked and how long did it take, and then we calculate that, as well as the cost of the factory. So, and that's what was Jim's point, the two different costs. And I think you could probably, it sounds like you've got a bunch of pretty good kids. You could have them do a Tetric's spreadsheet of just their parts. And I bet if you went to Tetric's website or a place that sells them, you could probably find a list of the major parts.
Or make them do it.
Yeah, give them. Right.
And if it's a bag of 50 and it costs, $2, and they've got to figure out how much one costs, and they help you this first year get the cost of all your parts.
Yeah, no, I think that's probably the way to do it right there. Yeah.
One thing we have to do is there's some things that you cannot purchase them individually. They come in like a accessory set. It's a worm gear and this and this and this. So we have to take the price breakdown and then kind of figure out, this piece has some brass with it. It's a little bit more expensive. So there are some numbers that we have to kind of fudge, but I don't think it'd be a bad experience for the kids.
Sure. Yeah, that'll work.
Chris, did you want to take a look at that objective sheet we sent today?
The what?
That right there. So I think one of the big things is right now you're in a good place to start doing some practice on your own while your kids are finishing up this whole control system, to give yourself a little bit more time to absorb this next section coming up. Because for some people, the programming is hard enough. This CAD/CAM can be a little bit more overwhelming. So if you've got a chance to start absorbing or chewing through some of this at a better pace, that may be a really good option for you. For like right now, really the curriculum's kind of broken up into 9 weeks. You've got 9 weeks of Unit 1, you've got 9 weeks of Unit 2, 9 weeks of Unit 3, and 9 weeks of Unit 4. So that's really supposed to be the concept. So right now, coming back into my second 9 weeks, to try to get all this done, I have to be in what Chris has pulled up right now. Otherwise, there's no way that I'm going to get a lot of it done. But it also may be, if you look at the factory doesn't have to be 9 weeks. You may only want to spend 2 weeks on the factory. So there's a lot of flexibility that you have, but I would suggest when it comes to CNC, hand programming, trying to go through speeds and feeds where really our only component of math is, and then learning how to use the CAM software, whether it's HSM or whatever each person's going to use. If you're not in it by now, then I would at least go ahead and start trying to absorb as much of it as I could.
Yeah.
So basically start working through some of these activities on my own and trying to see if I can actually get some parts milled out. And
sure. And
if I would have my machine up and running, I would figure it out. I'll be honest, my very first year when I was doing all this, before I ever did anything with the kids, I was here after school running the machine, making sure that I had everything set up, that I was competent about how to set up my tool library and this and that, before I was going to have kids around me at the same time. It's a little bit different when it comes to VEX. I guess it's a philosophy. If I mess up there, it's not really that big a deal. If I mess up on my $14,000 to $25,000 machine, it's a little bit bigger deal, and I'd rather The first time I'd be the only one there rather than everybody looking over my shoulder.
Yeah,
Right.
and my first projects too, the first year I taught this, my first project was make a container, and it was this rectangular container, period. And that's what all the kids made. And you know what? They were so happy. They were so excited because it was a CNC container. And I look back on that
Yeah.
and I laugh. It's like, really? That's what I used to. And hey, it teaches the concepts, but the first time through, if you have to keep it really simple, keep it really simple.
Sure.
You still teach the concepts, the kids get the idea, and then you can get crazy as time goes on. But like Jim said, what we wanted to do tonight was give you a little bit more insight into all of lesson 2, 2.1, 2.2, and 2.3. Now, this whole thing right here is going to take, like Jim said, about 9 weeks. Generally, and I
Okay.
bet Jim does too, I bet I take about 12 weeks to do CNC because kids love it. So I generally
Okay.
spend a little more time here, and what I'll do is I'll spend less time with design flaws in mass properties because my kids know Inventor when they come to me. So this mass properties
Okay.
activity, they whip through it. How we
Okay.
make things, I spend a little more time. So you have to start thinking too, all right, how can I, if I'm going to spend more time here, where's it going to go? And Jim made a good point. At the end, if you didn't spend as much time on the factory at the end, that's fine. You'll be okay. You'll be totally okay. But we wanted to
So
give you
what's the factory?
all of lesson 4.4.
Oh, okay.
Okay, so all of lesson 4.4, instead of building a factory, in some years, what I've done is when it comes to 4.1 sim systems and integration of manufacturing, I haven't had the time some years, and I've done 2 or 3 CNC projects, and the kids get the same idea by just making a single cell with the VEX and the Lynx Motion robotic arms. So
Okay.
it depends on where you want to spend your time and what you're comfortable with and what you become good at. So we wanted
Right.
to give you ahead of time this week some resources so that as you move forward, you could, we gave you a link to how to install the software. So if you have a person who installs your software, not all of your IT people get this information, so they're just winging it too. So we
Right.
gave you the link to give to them for all of the worksheets on how to install the software step by step. And my IT
Okay.
guy says this is his manual. He uses these as his manual, and everything just works when he's done. For the
Okay.
most part, he hasn't said, yeah, I haven't heard him screaming or ranting or crying yet. So, and most everything works so far, so we're doing all right.
Oh, good, good. So I haven't
Um,
had any issues yet, but I might want to email that to my tech guys anyway, just so they have it as a reference in the
Good.
future.
Now, are your students going to have any inventor background?
They should. That's the
Okay.
one thing they seem like they got
Good.
from their IED class,
Excellent.
or one thing they've got from their previous classes with the previous teacher.
Okay.
And at the beginning of the year, because I didn't have access to the curriculum yet, I actually had them all redesign Monopoly or some other board game. Most of them did Monopoly.
Gotcha.
And so they made a bunch of little playing pieces. I mean, there was no assemblies. It was pretty simple, but some of them did some pretty elaborate little Monopoly men.
Oh,
So
nice.
they've even practiced it already this year. So, you talked about that one part. They are good with Inventor and they can fly through. I'm thinking, yeah, my kids will probably be able to fly through that too, just because that's what we did for the first 2 weeks.
Right. Okay, good. Good. That's excellent because here's Unit 2, and if you were to look
I
at this,
saved that mass property analysis.
yeah.
I saved that mass property analysis actually for days that I'm not there.
So do I. And I
Okay.
was just going to mention that because, I've got a conference coming up, and I'm going to save
Okay.
that for when I'm gone because I know all my students have background in Inventor, and they should be able to knock those off without me around. But to just a real quick overview, it looks like, so this is like 3 weeks, 4 weeks compared to, look at all, these are all, no, this is still 9 to 12 weeks, depending on how much time you take, because this lesson 2.3 is all G&M code in CNC machining.
Okay.
Quick overview of lesson 2.1. Lesson 2.1 has a design flaws activity with a PowerPoint. So it's a little activity about here's some poor design, why is this poor design, and how do you fix it? I
Okay.
generally whip through that
You
real
skip
quick.
that a lot?
What's that?
Oh, you just go through it quick.
I go through this real quick. And then the mass property analysis activity, it's build 4 parts, and the 4 parts are really pretty simple, and they have to look at the drawings and actually make the parts from the drawings. So they look
cool.
like they look like this. So, and the kids all cry, "Oh, I'm missing it." No, everything you need to make that part is there, and we've checked.
Oh, that's awesome!
Times.
I almost want to take that with my IED kids,
just
to practice having them look both with drawing to design and design to drawing. Anyway.
So that'd be great too, and then you just come up with some harder ones for sim class and pass those on to Jim and I so that we can give those to our bluebirds also. Because think about it, if you pass these down to IED, that's awesome, and we're having that problem now too. I'm giving some of my cool stuff for sim to IED, but then he's making some harder stuff for me. Like I'll probably do different ones because same thing. But if you come up with different ones, pass them on up. And here's the cool part is that after they make this, and they generally get this made pretty quick, but the math that goes along with it. What's the material cost of the part, assuming that the cuttings are remelted and the cost of mild steel is this? So they're using iProperties in Inventor to come up with all this information, the density, the mass, and the volume.
Right.
So they make this part, they go to iProperties, they check the properties of all of them, and then they have to answer these questions. What will be the volume of the box needed? Go ahead.
I don't know how much they've used iProperties. So does the worksheet have instructions to say go to iProperties to get this information, or would I have to review that with them or add those instructions in if I especially if I'm going to do like you and use it on a day I'm not around?
It's pretty simple, and there's also, while Inventor's loading, it's going to take a little while on my machine. There's a couple guys we know that made a website that has some pretty cool stuff on it, and if you were to go to their website under Inventor Solutions, you would find how do I make the parts for the mass property analysis activity. And this, I wouldn't give this to I don't give this to my students. And for a kid who misses a lesson or a kid who knows nothing about Inventor, these are step-by-step videos how to make this part. Step-by-step videos how to make each of these. I have some special needs students also that when they get to 1 or 2 of these, they may put this side by side with Inventor and actually use this with Inventor. But so that's there as a resource as well. But the reason I open this up is because there is a how do I use mass properties analysis in here also. So it shows.
So I could give them a link to that video.
Yeah, but
for instance.
And as soon as Inventor loads, I'll give you a short tutorial on how to do it. What's that?
I've used iProperties. I just don't know that my kids have because I don't. I wasn't there last year when they used Inventor, or 2 years ago. So I don't know if that was something. And I don't want to badmouth my predecessor, but I keep getting a lot of things said by students and parents and teachers about how he didn't really do the curriculum, and there's a lot of time wasted and things like that. And I just really don't have a good handle on where they are, and my suspicion is a lot of stuff got missed.
And that's good that you're looking towards figuring out what it is they did miss, because chances are you're right. And it's better to be prepared for it than it's always a nice surprise when they say, oh no, yeah, we've done that, here, it's right here, this is how you do it. But those nice surprises are usually pretty rare. So here's an example of the pipe support, which is I think model number 4. So a student builds this. Pardon me. Student actually builds this. Once they get it all done, you can go up to the I, and you go down to iProperties. And so iProperties has a tab over here called Physical. This is all the stuff, the summary. You can make kids fill this stuff out if you want, and where it saves it, work in progress, blah, blah. The big thing that I have them do, I don't do anything with any of this except the physical.
Okay.
And it does say in the directions what each part is made out of. So they have to go and they have to pick the material that it's made out of. Just know that when they go from mild steel, it's alphabetical, but steel is under, mild steel is under steel, comma, mile. It's there. And soft yellow brass is brass, comma, soft yellow.
Right.
So you pick the material that it's made out of, and then you can say apply, and it will tell you the mass, the area, and the volume of the part. And here's the other kicker. The last part says to be made in metric. So that's why this is in kilograms, in millimeters per square centimeter, or millimeters per square, or millimeters squared in cubic millimeters. So that's why these are all in kilograms.
Except density is always in metric or something.
Right, and density is always going to be in metric.
Okay.
So you've got...
I think that was a question either on IED or something a couple of years ago, as they gave them a density question in metric and they had to convert that into standard.
Real? Oh, yeah, you're right. I do remember that. I do remember kids saying something about that. In the sheet that you get with all the formulas on it has that standard conversion, and they just have to know how to use it. So once they make the part, so that particular part's this one right here, they have to answer these questions. What's the material cost of the part, assuming that the cuttings are remelted and the cost of soft yellow brass is $13.50 per pound? What's the material cost if the cuttings are not remelted? So you have to figure out what's the volume of this after you've machined it. So I'll have kids who go back and make the part from which this came, and then subtract, then do the iProperties of that and subtract the two.
Okay.
But the smarter kids realize that it's just this dimension by this dimension by this dimension multiplied.
Sure.
And they're done in 10 seconds versus 3 minutes, because the other kid...
So the assumption is this is machined out of a solid rectangular prism or whatever.
Correct.
And then if it's remelted, we're saying, we're recovering all that material, and if it's not, then these shavings are pitched.
And really what you're trying to do is you want them to get the gist of why it is so important for us to reclaim and get back cost for each product. And when I do recycle all my material from my machine shop, I get nickels and dimes for it, but when you figure how many pounds of it I'm sending in, I'm not getting something back from it. That's so much money that I'm throwing away, and there's really good questions here. What I have my kids do on that document that Chris is looking at, I have them delete that photo with all the dimensions. They give me a screen capture of their file and just replace that.
Nice.
And then over on the side where it says model material, I have them delete all that information, and they give me a screen capture of the iProperties.
This one right here.
All they do is go to another kid, get the numbers, and they're done.
Have you ever used the snipping tool before in Windows?
Yeah, absolutely. I was teaching them all how to use that not too long ago in my IED class. So
snip that out, put it right in the space.
So that's cool. So you're saying you make them snip it because you feel like that's a good way to cut down on the cheating?
Right, and I also have this part. I've made this part, so I know what the mass, the area, and the volume are, down to the thousandth of a cubic millimeter. So when they make the part and it's not that, I'm like, no, sorry, you're wrong. No, I'm not. Yes, you are, because it's not this. And once the kids figure out what dimension they have wrong, it always comes out to what I have. So
Right. The whole thing. You need the center of gravity and things as well.
Right.
If the kid shifts a hole, as far as they're concerned, the surface area and everything's going to be identical. You can change there, but it will manipulate the center of gravity and those types of things.
If they do what?
If this
Like
hole,
if that hole there on the bottom was shifted, if he moved it to a different location,
back here
that wouldn't
somewhere.
Okay.
area, volume, mass, none of that would be any different, but the center of gravity would be different.
Okay, yeah, I'm following you now.
Yeah, so the kids dislike doing the math, but like Jim said, it's very valuable in terms of lean manufacturing. You're talking about recycling material. You're talking about
Right.
all these different things. The costs it ties back in, ties right back into the costs. So this is a really cool project. So if you do come up with some of these with some other math problems, let us know. We'd love to.
Okay.
We'd love to be able to use them too. I've got a couple, and I can see if I can find them, and I'll share them with you as well. I just have
We're
to.
just now in my manufacturing lab, we're just now getting to the point to where we can use our kiln, and all the aluminum that we machine, we're starting to reclaim and be able to turn back into usable material to make some other projects out of. Just looking at how much my aluminum costs, without reclaiming it, there's so much money that we're just throwing away every year.
Right, right. And we take a field trip to a local company where right behind all the machining centers is a bin collecting all of the scrap. And so if we come later in the afternoon, that bin is full of scrap, and they're like, holy cow, yeah, all of that stuff is going back and getting melted, and they're getting their money back out of that.
Right.
A good video, too, is the Apple video for their, not the MacBook Air, the I forget which one it is. The MacBook Pro. So if you go find the video of the MacBook Pro being machined out of a single billet of aluminum, every scrap of that aluminum that they cut out of that gets remelted and used on the next computer. That's their process. So it's a really good video that says, hey, look, in theory, here's how it could be done. Is it a good way to do it? I don't know. They say they're saving money, but I don't think that they are. That's another story. But
by machining it all out of one piece, you don't think that's a...
Oh no!
Right.
Oh my gosh! I've got a Mac. This presentation is being done on a Mac. This Mac is the best.
Long to load.
Right. This Mac is the best laptop I've ever owned, hardware-wise. And the reason it took so long to load is because I have too many things going on. But, it works very well. I just think that I don't know. I mean, you can't tell me that they can manufacture, and their product costs a lot more too. So you got to look at that as well. So does that factor into the cost of the, and the kids and I have decided that yes, of course it does, because that process, that piece of aluminum is expensive. And even though you're cutting all that out and remelting it, if you do the math, it's still costing you more. So because of the process, you have to pay for the heat to melt the kiln to melt down the aluminum into another billet, and then you have to machine that billet. So somewhere, where's that cost going? And, okay, so maybe that's why a Mac laptop costs more than a PC.
Right.
And sure, of course it might be. So that's a good way to look at it too. So if we go back home, so that's really all of lesson 2.1. Lesson 2. Well, we have about 3 minutes left, so why don't we end it there, and we'll talk a little bit next time about lesson 2.2. And really, lesson 2.2 is about creating prototypes. It's about rapid prototyping, manufacturing processes. We'll talk about how we do this in our respective classes. Both of us do it a little bit differently, and because Jim has a full machine shop at his disposal, and I have some machines from back in the day when we were tech ed, I do things differently in my classroom too. So, it depends on. Do you have an old injection molder from the old days by any chance in your lab?
I don't think so.
No?
No, I mean, I was hoping, I bought a bunch of machinable wax, and they advertised that one of the things you could do with that was epoxy molding.
Yeah.
But of course, it wouldn't be injection molding, but I was hoping to get some epoxy resin and have them make some molds.
Awesome. That's pretty cool.
Point.
Yep.
I started molds with my wax, and I get it from Pittsco. It's It's material for making fishing worms. It's just a catalyst material. It's two materials that you mix together, and once you mix them together, you pour them into the mold, and they come out as rubber.
Okay. Okay. I hadn't really got. I started to look for something like mine was more like it would be more of a hard plastic. I think.
Yeah.
What I was looking at.
And I've done that before with epoxy resin and made knobs. A kid made a knob for a camp stove.
Okay.
So that works too.
I mean, I was kind of hoping to revisit this whole monopoly thing and have them build molds for those, and then
Sure.
you know, stamp out their parts or whatever. But most of them made pieces that I think are far too complex for me to try to want to machine molds for. So
Right.
we probably won't do that. They were cool parts, but not something I want to try to make molds for.
Right. Right. You'd think that those rubber worms would be a little bit easier to find, Jim.
I don't remember what it's called. It's just
Yeah,
it's not a mold. It's just the material to make the worms.
yeah, we do the golf tees, so I'll find it. We'll find it, and then I'll post it in a comment so that because I want to get into that again too. That's something I'd like to do for molding. We do one of my other classes, my production systems class, we actually use pewter, and the kids make these little pewter figurines, and we use rubber molds.
Cool.
Yeah. So I'll do a Fast 5 at the beginning of class period. I'll demonstrate this, and then while they're doing a research activity, they can get up and make, mold something. And then the next day or a couple days later, we do the injection molder. So because I have these things, we'll talk about that later, but because I have these things, my kids can experience it.
Right.
And it makes it I think it makes it a little more fun if they get to take home an injection molded golf tee or a screwdriver than watching a video on it. Although the videos, I guess, work too. So
I would love to. I mean, I think the injection molding would be cool. It looks like, is that a metal plate there? They machine out of metal?
No, I haven't. I've never gone that far. We have an old injection molder from my ASCO, and these molds were bought at one point, and I just have these molds, and we take these molds, and the kids just go back and they make an injection molded screwdriver or a golf tee so that they know what the process of injection molding is.
Okay, so you have prefabricated molds, and they just get to play with them.
Yes, it's good playtime. Cool. So because lesson 2.2, I don't want lesson 2.2 to take up a lot of time because I want to spend more time in lesson 2.3. So we'll talk a little more next time about 2.2. Get into 2.3 and talk about CAD and CAM.
Sounds good.
Sound good?
Sure does. Well, thanks. I hope this video is useful to the people who weren't around. But
I most certainly.
It was a good conversation for me.
I think so too, and I think it'll work just fine for the people that couldn't make it.
All right.
All right. Well, hey, have a great night.
Thank you, gentlemen.
You're welcome.
You too.
Bye-bye.